Good afternoon. Hi, how are you? Thank you. Yes, I hope all of you are also very good. Thank you very much. Thank you.
Sir, very good afternoon. Yeah, I'll be waiting, sir.
Yes, madam, yes.
Yes, sir.
Very good afternoon to one and all. First, I'd like to thank the management and the organizers for giving me a nice opportunity to take part in this grand conference. So everyone who remembers his own education remembers teachers, not methods and techniques. The teacher is the heart of the educational system. So with these passionate words by Sidney Hook, I'm pleased to introduce our today's chief guest, the outstanding speaker, come learner, Professor Rosana Rodríguez-López, a senior faculty of mathematics from Institute of Mathematics, University of Santiago de Compostela, Spain. Rosana Rodríguez-López has a doctorate in mathematics, obtaining her doctorate in 2005. She is the former member of Department of Mathematical Analysis and currently a member at Department of Statistics, Mathematical Analysis and Optimization. She is a research professor and vice dean of the Faculty of Mathematics and coordinator of degree in mathematics. She previously enjoyed a training grant for research personnel and was a teacher in secondary schools. Noteworthy is her work as a disseminator, primarily at the local level of city of Santiago. Her fields of research are differential equations and fuzzy mathematics. She obtained worldwide recognition from the mathematical community in 2005 when she published the article Contractive Mapping Theorems in Partially Ordered Sets and Applications to Ordinary Differential Equations. So together with Juan Jose Nieto. So I'm correct with Spanish pronunciation, right? It is Juan Jose Nieto. So this work is one of the most cited in mathematical academic field of Spanish origin. Since then, she has signed about 70 works of mathematical analysis. She has published more than 86 research papers to her credit in international journals and conferences. She has been worked in 24 research projects and produced numerous results in emerging research area. So with this short note, may I invite Professor Rosana Rodríguez-López to take over the session. Please welcome, ma'am. The session is yours.
Thank you very much. Thank you very much to everybody. For me, it's an honor and a pleasure to participate in this very nice meeting. I would like to thank PPG College of Arts and Sciences, all the authorities, professors, all the members, and all the participants in this very nice event. And a special thanks to the organization of the conference, all the advisory committees, and also especially to Dr. Hari Krishna, who contacted me. Thank you very much, and also Professor Marshal Antony for his very nice presentation. It's my pleasure, and I want to express my best, give my best regards and best wishes for all of you and all your families. So I will try to share my presentation now, and I hope you are seeing the presentation.
Yes, ma'am.
Thank you very much. Okay, so my talk is about some fixed point results in abstract spaces with some applications, and the talk is divided into these four parts. Well, some of them very brief, and others are more extensive. Starting with a very brief introduction about why to consider this kind of fixed point results in abstract spaces. Mainly the motivation is going to be the study of some mathematical models of uncertainty. I shall give some very fast presentation, very quick presentation of some concepts needed. And I'm going to present in the third part some fixed point results in abstract spaces, which will be used to give some applications to differential equations of arbitrary order in this context of uncertainty. So all of us, it's widely known the importance of fixed point theory as a tool for studying the properties to the solution of many differential equations, to study some properties of the solutions, such as the existence of the solutions, the uniqueness, the localization of the solutions, sometimes the multiplicity of the solutions. And most of the results which are provided, fixed point results, are established traditionally in some kind of vector spaces with particular structure, which is normally the one given by a norm, which is complete. With some exceptions, of course, the classical Banach contraction mapping principle is valid for complete metric spaces. But many other results, like Schroeder theorem or Krasnodębski theorems, are given for Banach spaces. So, what is the motivation for providing some fixed point results in other spaces which can be somehow more general? So the idea is to provide some fixed point results which are valid in spaces where you don't have a vectorial structure itself, but the structure of a cone. It's you don't need the whole vector space, some of the properties of the vector space, but not all of them. And especially the models are in this context when you want to study some equations given in a framework where the uncertainty plays an important role. I mean, you are going to study a problem, you have to make some measurements, you have to distinguish some real factors to determine the influence of these factors in the model, and sometimes these factors cannot be precisely measured, and then they are imprecise, or there are some data which are imprecise. So there are many possibilities of studying this kind of problems. The approach I am following here is not probabilistic, is not a stochastical type. Is the study of uncertainty from the point of view of subjective elections, maybe more than probabilistic issues. So the main results I'm going to use in this talk is one extension of Schroeder fixed point theorem to what is called semilinear space. This is has been given by other authors, and I'm also going to present an extension of the Krasnodębski, one of the versions of Krasnodębski fixed point theorem, in the particular case of one semilinear space, which is given by the fuzzy metric space. And the application I'm going to give is to the study of fractional differential equations under uncertainty, which we, all of us know, that they have been studied as adequate models to describe hereditary properties and memory effects in different materials and processes in many areas. Some of them are collected there. So this is one of the fields of study which nowadays is attracting a lot of research also. So what kind of uncertainty I am going to consider? I'm going to consider a space which is going to be denoted by these letters. It's R, the real line, but with an F, which denotes the fuzzy real line, which is, it consists of the elements, which are functions defined in the whole real line, with values between 0 and 1. And these elements, what they describe is the different degrees of membership that a property may have for an element. I mean, if you want to describe if a person is very tall or is tall, or if this young, for example, These are concepts, and there are many concepts from the linguistics that can be represented appropriately using a function of this type that has different sets representing different degrees of membership to a certain property. Normally, for the mathematical basis of the space and the good properties of the space, we are not considering all the possible functions with values in 0, 1, but normally we consider only the ones that satisfy these 4 properties, which are the normality, I mean the existence of an element in the real line attaining the value 1 through the function, and the upper semi-continuous character. I have here there is a picture of a continuous one, which will be important afterwards in the development of the results, but theoretically we only need to consider upper semi-continuity. The fuzzy-convex character, that is, despite of the name, it represents not a convex but a concave function from the point of view of the function, and which is compact supported. I mean, the closure of the elements with positive values have to be bounded. So with these 4 properties, what we have is that we are not going to consider the function itself, would imply to work in a functional space, infinite dimensional. We are going to cut these elements into levels. So for every value between 0 and 1, we make a cut, and we select the points, the interval of points, whose value through the function is at least this value alpha. So for each alpha between 0 and 1, we have the cuts of this element. So we are passing really to work with intervals. Indeed. All these properties guarantee that these cuts are compact intervals. So in general, we are going to pass to these alpha cuts, which is the set of elements for each alpha, the set of elements with values greater than or equal to alpha, except in the support, which is going to be the closure of the elements where the function takes positive values. And in this space formed by these functions, where we are going to consider these cuts, we can define some operations which come from the set operations. I mean, we can obtain the cuts of the addition of 2 elements just by simply adding the cuts, the corresponding cuts, or something similar for the multiplication by an scalar lambda. The good part of this space is that we can define a metric very easily, which consists on calculating the supremum in all the levels of the Hausdorff distance between the cuts of both numbers, which are intervals. So we are using the Hausdorff distance on each level, and this is well defined. It's a metric, and it gives a complete metric space. This structure is enough for applying, for example, a fixed point result of the type of Banach contraction mapping, of course. The distance has another interesting properties, such as the invariance by translations. If we add W on both sides, we have the same value, and also the positively homogeneity, because the non-negative scalars can go out easily. If they are negative, you have to consider the absolute value. And another properties, such as what happens when you multiply a fixed fuzzy set by scalars, different scalars, you have this other property and this other one, which is somehow related to the inequality, the triangular inequality, and to have an estimation of the distance between additions of elements. So the structure is not vectorial, but it's not so bad. It's not so bad. However, we cannot apply, if we can consider a differential equation on a set of this type, but we cannot apply many of the fixed point results available, because they would need the structure of a Banach space. How to define a differential equation in this space? There are many approaches and continue evolving also. One of the that has attracted most the attention is the one based on a differential equation that considers the concept of differential of a fuzzy function, different concepts of derivatives. How to consider a derivative for a function with values in a space like this. So since the 80s, many different definitions have been arising to study the problem from this approach. There are other approaches like Sade extension principle. In fact, Sade is the person who proposed the concept of fuzzy set in 65. And also the concept, the approach of differential inclusions. There are different approaches. Sometimes they provide different type of solutions. So, well, you have to select carefully the type of approach. And if you select the study through the use of differentials, you have to be careful with the type of derivative you select because some of them may have some drawbacks. So I will only use the simplest type of derivative just to illustrate the process, because we are going to consider also a fractional differential equation using this concept. So I'm going to choose just the one of the first derivatives, H derivative, based on a concept of difference given by Fukuhara, and a strongly generalized derivative, which is due to Bede and Gall and other authors have been providing different properties for this derivative. There are other different notions for differences for these spaces and derivatives. And very recently, we have also worked on a new concept of derivative, which is based only on the properties of the distance in the space. But I'm going to present one of the simplest concept of derivative in this space. And so the main difficulty you find in this kind of spaces, which doesn't have a vector structure, the problem is the subtraction. There is no proper subtraction, because if you use the subtraction given by the addition of the opposite, since through the cuts you are working with intervals in the one-dimensional case, if you add, for example, the interval 0, 1 plus the opposite, you are not going to have the 0. This is one of the main difficulties to work with this kind of sets, to work with interval differential equations or with fuzzy differential equations. So one of the first ideas of taking a difference is precisely to say that the difference of u and v is an element set provided it exists, such that u is the addition of v plus z. So using the addition to define a difference, okay? This way, if you have u minus u, you have the 0, and you can have some kind of development of calculus using this difference. The definition of strongly generalized differentiability from that was proposed by Bede and Gall in 2010. If you see, the concept of derivative is analogous to the classical derivative by avoiding the problem that the difference is given into the definition. I mean, it is not the same to put this expression than to put the opposite of the difference reversed. So you have to distinguish several cases. That is the summarizing. This is the proposal of the derivative. So depending on the side you are considering in first place, in order to get the difference, you have different types of derivatives, which is 1, 2. There is another two concepts. There are two another concepts that mixed these properties and give way to something which is called the switching points in the differentiability. but just to illustrate one simple derivative in order to present the next concept, this notion will be enough. So what happens with these fixed point results I was mentioning? Of course, the Schroeder fixed point theorem, one of the version is written here, says that any compact, convex, non-empty subset of a norm space has the fixed point property. And there is another version where the compactness is moved from the set to the mapping. If we want to apply some kind of these results in the context of the spaces I was speaking about, you find that you don't have a vectorial structure. You don't have a vector space. But even if it is not a vector space, it has a structure of a cone. It behaves well with addition, and it behaves well with the multiplication with non-negative scalars. Not with the negative, but it is enough to work with the non-negative ones. So a concept which is used to extend Schroeder fixed point theorem to this kind of abstract spaces that include the one I was presenting before is the concept of semilinear metric space. It is an extension of a vector space in the following sense. A semilinear metric space is a space that has an addition operation and a multiplication by an scalar by non-negative scalars. And you have a metric D defined in the Cartesian product of this space S with non-negative values. And to this distance, we are going to require two properties that I mentioned before, that they are fulfilled for this particular example I showed, which is the invariance by translations and the positively homogeneity. I mean, if you make a translation of A and B through the element C, the distance is exactly the same. And if you have a lambda non-negative coefficient, this coefficient goes out of the distance without problem. So this is a semilinear metric space. If with this distance the semilinear metric space is complete, this is going to be called a semilinear Banach metric space. So in many senses, I am going to ask the metric to be complete also. But this is the concept of semilinear metric space. Okay, so another property that has to be added to these ones of the semilinear metric space in order for the main results to work is, it is called the cancellation property, which is like if you write A plus B equal to C plus B, you can cancel B and then deduce that A is equal to C in this space. This cancellation property is also fulfilled for the case of this space I was speaking about before, for the case of the fuzzy real numbers. So with the structure of semilinear metric space, we are going also to impose the completeness of the metric, and this cancellation property, it is possible to give an extension of the Schroeder fixed point theorem. And this extension was proved by Professor Agarbal, Arshad, O'Regan, and Lupulescu in 2013. And it says that if you have a non-empty, closed, bounded, and convex subset of a semilinear Banach space, I mean a semilinear space with a metric which is complete, having the cancellation property, and you have a compact mapping from this set into itself, you know that this mapping has at least one fixed point in V. So this is an interesting result to be applied in to study of differential equations where the base space is a semilinear space like the one I spoke about before. Another recent work by Professor Long and Dong from Vietnam, they also give an extension of Krasnoselski fixed point theorem in the context also of semilinear spaces. And we have recently worked on an alternative proof of the result specifically for the type of fuzzy metric spaces. It's a recent paper which is submitted at this moment. So the idea of this theorem is the following. We are going to work with these fuzzy numbers, but only the ones which are continuous. You remember that I have a picture at the beginning, and I was the picture was in fact a continuous fuzzy set because the picture was configured by a continuous curve, a line, or whatever. It was continuous. It is enough to be upper semi-continuous for the definition, but for this process, we need to work with continuous functions defining this fuzzy number. And this extension of Krasnoselski fixed point theorem for this fuzzy metric space says the following. If we have M, a non-empty, closed, and convex subset of the set of the continuous functions from a compact interval into the continuous fuzzy number set, and you have two maps, A and B, each of them are going to map M into the semilinear space in general, but we are going to impose that when you apply A to an element X, arbitrary element, and calculate the addition of the result of applying V to another arbitrary element in M, the result has to be in M, because we are going to work to look for fixed points of this expression, solutions to this equation. So this is for the good definition of the mapping. And this is the classical Krasnoselski fixed point result, where you have a compact and continuous, of course, part, and another part which is a contraction mapping. You have the sum, the addition of a compact part and a contractive part. Okay, this is a result valid also, of course, in the context of Banach spaces, but also for this particular space, which is not a Banach space, but has the structure of semilinear Banach space, in the sense that the metric is complete. It is possible to say that there exists an element which is a fixed point of A plus B. I mean, it's a solution to this equation. So just to give a very fast explanation of the proof. We are going to use first the property of contractivity of B. So first, we consider a fixed Y in this part, and we change the name of the variable in these others. So we are considering the problem to find the sets that satisfy that set is equal to A of Y, where Y is an element of M, which is fixed, plus B set. Okay, since this part is fixed, it is very easy to prove using that B is a contraction, and we have a complete metric space, and that there is a unique, for this Y fixed, there is a unique fixed point that we are going to represent by psi of Y. Okay, for Y fixed, there is a unique fixed point denoted by psi of Y. Okay. In this particular setting, you remember that when you have this addition of numbers, I can consider the H difference of this element and this element. So I know that identity, in this case, sorry for the coincidence, this is an interval, and this is the identity operator, the identity mapping. The identity minus with the H difference, B, it exists. And we have the expression written in this form. So the only thing we have to prove is that the identity minus B is continuous. This is quite obvious. It's injective, and using that B is a contraction is very simple to use to prove that this is injective. So surjective to the image. So I can construct the inverse And the inverse, also by the contractivity condition of B, is going to be continuous. Okay? This is going to be continuous. So, if you see this composition, you have this part that is going to be compact and continuous, and this part is going to be continuous. So we have sufficient conditions to apply Schauder fixed point theorem for semilinear Banach spaces to this operator. So we know that it has at least a fixed point. So there exists at least y0, such that if we put here y0 and also here, we have the same exactly as y0. Okay, but then the proof is finished. The proof is finished because psi of y0 was the unique fixed point of, in this expression, putting y in this part fixed. Okay, if we put here a of y0, phi y0 was the unique solution to this equation. But now we have proved that phi of y0 is y0. So we have at least one element satisfying this condition. So you see the proof is straightforward based on Schauder fixed point theorem for semilinear Banach spaces. So these two results can be applied to many differential equations in this kind of particular spaces where you don't have a vectorial structure. So just to illustrate one of the applications, I'm going to show a differential equation, how to consider a differential equation from this point of view in uncertain spaces. The concept of fractional integral and derivative has to be defined for these special spaces, but it is based on the classical Riemann-Liouville integral and derivatives of fractionary order, which all of you know. Here you have an integration, and gamma is the gamma function, which is an extension of the factorial. And I'm going to consider the real part of alpha positive, and the derivative, the Riemann-Liouville fractional derivative of order alpha of a function f will have this expression where n is the floor of alpha plus 1, the integer part of alpha plus 1. So first we integrate, and then we make the derivative of the ceiling of alpha, really. So these are the classical concepts, but of course we can find all the properties in many references, many relevant references about fractional calculus. And for the particular application I am presenting here, the motivation, one of the motivations was trying to extend the results given by Del Bosco and Rodino that were given for a fractional differential equation, a classical fractional differential equations, and our motivation was to see if some analogous properties could be studied in the context of uncertain differential equations. Another important reference is the development of the concept of solution for fractional differential equations with uncertainty, given by Professors Agarbal, Lasmikantan, and Nieto in 2010, and a work by Professor Arshad and Lupulescu that gave some of the properties of the fractional operators and use it for studying some differential equation in this context. Okay, so to recall the spaces used, we are going to work with continuous fuzzy sets, continuous fuzzy numbers. I mean the one whose representation is given by a continuous graph, saying it very fast. You have the structure of the complete metric space. For this distance I defined previously, based on the Hausdorff distance between alpha cats. And we are going to consider a type of weighted space. I'm going to consider functions which are continuous in a certain interval, but not necessarily at zero. We don't need the definition. We are going to allow singularities at this point with values at the continuous fuzzy sets, but with the restriction that when you multiply the function by the power of t given by this number, you get a continuous function in the compact set. It's a kind of regularized version of u multiplying by a certain factor that makes singular things in continuous functions on compact sets. So even if the final solutions of our problem may have singularities at zero, we are making this trick to convert things into continuous functions in order to choose spaces with better properties. So in this space of regularized functions, we have also a structure of a complete metric space, just taking the supremum or the maximum norm, not of the distances between u and v, but regularized functions. So this is well defined, and it allows to apply many mathematical tools. Of course, we don't have a vector space. Still, we don't have a vector space because the functions take values in this space, which is not a vector space, but is a semilinear Banach space. And this is also a semilinear Banach space. And we have all the properties needed to apply these fixed point results we were mentioning. But since we are going to use compactness concepts, we also need to have at our disposal some definitions about what is a relatively compact set in this space, or in the space of the continuous functions on a compact with values in this space. So for the space of continuous functions in a compact with values in a metric space, we have the traditional Ascoli-Artela theorem. So we only need to know how to obtain relatively compact sets in this space of real fuzzy sets. And these concepts were developed by Professors Román Flores and Rojas Medar in 2002. And they defined the analogous to the totally boundedness, equicontinuity, and uniform equicontinuity in this context. In this context, the important concepts are the compact supported character. A subset in this space is said to be compact supported if there exists a compact set that includes the support of all of the elements of A. I mean, the closure of the points where Y is strictly positive for all the elements. This is somehow the concept analogous to the totally boundedness. And also, what we need to develop here is a kind of equicontinuity, they also did in this work. A is said to be level equicontinuous at alpha 0 if, and you have an analogous definition, but level-wise. For every epsilon, there exists delta, such that if alpha is close to alpha 0, then the Hausdorff distance between the cuts are also close in these terms. Okay, so level equicontinuous on all the interval, it would be level equicontinuous at every alpha on the interval. So these concepts are helpful to work with, in order to obtain some relatively compactness criteria in this set. They did it also in this work, and they proved that if you have a compact supported subset of this space, the following assertions are equivalent. It is equivalent to say that here A is referred to a set, this notation. Relatively compact subset in this space is equivalent to the level equicontinuity if we have the property of compass supported. In fact, the first assertion implies this and this. But for the converse, we need to assume the compact supported character added to the level equicontinuity, we deduce the relatively compact compactness property. So this is an important tool also to work with compact mappings in this context. And what is a compact mapping? A compact mapping from the Cartesian product of a compact interval, real compact interval, and this set of continuous fuzzy sets into itself is compact if it is continuous, and it maps bounded sets into relatively compact sets. So it's somehow the classical definition for a compact set. Okay, if we want to define differential equations in this setting, we need to provide the notions of fractional integrals and fractional derivatives in this setting. So with the integral, there is no problem because we are going to work with the concept of Amann integral, which is for every alpha, we make a cut. If you cut in levels a function with values in this set, you have many functions with values in the closed and compact subset of the n-dimensional Euclidean space. So if you ask that all the cut functions are Lebesgue measurable, this is called that f is strongly measurable. To define the integral of f over an interval I, you only need to do the integral of each level function. And on each level, you have to consider the integral of the integrable selections for the multi-valued mapping. Mainly, we are going to work with continuous functions. So if you have a continuous function, everything is going to work great. If not, at least you have to require something called a function which is integrally bounded, and the notion of strongly measurable I said before, provided that the integral is in the space, in the proper space. But if we work with continuous functions, then everything is going to work. Of course, we also denote as L1 the space of Lebesgue integrable functions. And this notion of integral has all the good properties expected. I mean, it is linear, the distance between two functions is integrable, and we have this estimation for the distance between two integrals. So all the properties expected work. So it is possible to define a fuzzy fractional integral of order Q with the same definition of the classical definition of Riemann-Liouville integral, but considering this integral as an Amann integral, provided it is defined. In the work by Arshad and Lupulescu, they prove some interesting properties of this definition of integral. For example, the additivity, which is a quite important property also in the classical fractionary case. And what happens with the derivative? The same notion that we considered before can be used. Here it is given only for orders of derivation between 0 and 1. And in this case, this derivative denotes one of the concepts of derivative for functions with fuzzy values. At the beginning, I was saying that I was going to take just the simplest one, just to illustrate the procedure. So this could be, for example, the one derivative we spoke at the beginning. But the style of the definition is the same. And many of the properties expected are also fulfilled. For example, the linearity. And another property which is very important for solving fractional differential equations, it will be also for the case of uncertainty differential equations, is the left inverse character of the left inverse character of the integral and the derivative. We know that it is not true in the fractional calculus that they are inverse, only inverse by one side, and this is the same case here. So, to consider just some result for a differential equation of fractional type under uncertainty, I am considering just one of order q with q between 0 and 1 given by a continuous function f, which is not required to be even defined at 0 at the points of the type 0x. Just continuous if we remove this line. And of course, a solution of this problem is going to be a continuous function. It can be singular at 0, no problem. It has to be Lebesgue integrable with continuous fractional derivative of order q and satisfying the equation. And using the left inverse character of the integral, instead of studying directly this equation, we are going to study an integral equation associated of this type. U of t equal to the integral of order q of f t u of t. If f is suitable, if you have a solution to this problem, you are going to have a solution to problem 1. If f is such that it takes continuous functions into functions which are continuous and Lebesgue integrable, you're going to have this, the pass between these. So just to explain very quick the process, in order to allow f to have the more general properties, the same as we did with the function u to be expected as a solution, it could be singular at 0. We would expect something similar for the f. We are going to allow general properties for the f. And so, when considering the integral equation and writing this integral operator through this expression, we are going to insert in the middle terms of the type s to the power r and s to the power minus r. The part of s with the power minus r is going to be put in the integral part. Why? Because of the properties of the integration, the properties of the gamma and beta functions, you can use this term in this part. This allows to put another s to the power r besides the f in the, here I'm only writing one part of the mapping, and the other part, it's a kind of Nemitsky operator. But we are going to put a power r, no negative, in general positive, so we are allowing more general properties to the f. And the proof is, it has a lot of details, but the idea is to prove the classical properties expected for these mappings. I mean, A is well-defined and continuous. To prove that A is well-defined, we only have to prove that it takes continuous function into continuous functions. In fact, if you take a continuous function fixed, the image is not going to be only continuous, but it's going to be uniformly continuous. And this is a property of the integrals we have here. I am not going to go into the details, but the idea is that. To prove the continuity is very simple also, just by considering a sequence tending to V, it is easy to see that A of Vn tends to A of B just by direct integration and here. Some other properties which are interesting. A takes bounded sets into bounded sets. This is quite simple. The estimation is variated by a quotient of gammas. I'm not going to speak about the details. And very important property also, it takes bounded sets into equicontinuous sets. The calculations done for proving the good definition of A, almost the same, are useful to deduce also this property. So I'm not going to say anything else. especially the following, the property E. The property E is very important because it is the one that is going to close the loop and to provide the compactness of the composition of the Nemitsky operator and this one, which is if you have G such that the images of all the elements of G on the interval 0, 1 is compact supported and level equicontinuous, then the mapping A takes G into a relatively compact set here. And this is the key point. So to prove that A of G is relatively compact in the set of the continuous functions on a compact set with values in this metric space is the application of the Ascoli-Arsalat theorem. We are going to see that if it is equicontinuous, and for every T, it is relatively compact in this set. But we already know that if G is bounded, A of G is equicontinuous, so the first thing is very easy. And for the second thing, when applying to T, this statement is equivalent to the concept presented before, saying that it has to be compact supported and level equicontinuity. And it is easily deduced. I don't want to make a very long this part because it has a lot of details, but it is very easy to prove that for each T fix, A of G on T is compact supported, it's just calculation, and level equicontinuous. It's just to put the definitions, to use the distance, and to be using all the inequalities we have around. So it's quite simple to prove the good properties of this part of the integral that includes this part which has a term, a negative power, or 0 maybe, power of the variable. The other part, the Nemitsky type operator, we consider a ball, the set of continuous functions that are at distance less or equal to r from 0, considering this supremum distance. And we define n like this. It's just the f with the regularization term in order to allow better, more general properties for function f. Okay, f is going to be, we're going to ask this function to be continuous, so this is going to be well defined. We also consider here another ball, which is a ball not in the space of continuous, but in the space of the fuzzy sets with the same radius. And for this part of f, we can see the important properties in order to get a composition which is a compact mapping. We are going to ask not f, but the regularized function to be uniformly continuous and bounded in order to get the continuities and boundedness of this mapping n. And maybe you are thinking, why uniformly continuous? The problem, why is not enough continuity? The problem is that the closed balls in this space are not compact. That is the problem. So when we are working with spaces where we are not sure if we can consider neighborhoods which are compact. I mean, when we are not working with locally compact spaces, normally the restriction of the uniform continuity has to be imposed. No? And the other thing we are going to need is something in relation with the FR, the compactness of FR. So another property is that if FR maps the Cartesian product of this compact interval times the ball of radius r in the space of continuous fuzzy sets, is compact supported and level equicontinuous, then n of omega is going to be relatively compact. So the main hypothesis, and it is quite straightforward, the proof, I'm not going to stop in the details, I am running out of time, is the uniformly continuous unbounded character, not of F, but of the regularized FR, to prove the continuity and boundedness of N, and the fact that this function takes this bounded set into a compact supported and level equicontinuous set, which is really the compact character of FR. So finally, collecting all this information together, we can prove some results, for example, this one, for an order of differentiation, of derivation, Q between 0 and 1, if we take this R, which is going to be helpful for the weighted space, non-negative, less than Q, and you have a continuous function, but not necessarily on t equal to 0, if the regularized function is compact and uniformly continuous, here, the fuzzy integral equation has at least one continuous solution defined locally for a suitable interval of the type 0 psi. And the idea is just to consider a ball in the space of continuous. At the beginning, we can work in 0, 1, which is a closed convex subset in a semilinear Banach space, and to define the operator, which is split into these two parts I was mentioning. But the composition, using all the properties seen, is continuous and compact. So we can apply, for example, Schauder's fixed point theorem for semilinear Banach spaces, and we have the existence of a solution provided that the operator takes the set into itself. So maybe we have to restrict to a place which is smaller, in the sense that we are going to stop before A, or before 1, in this case. And if F is suitable, we have a solution to the differential problem. So just to show the two references involved in this, and I want to express my thanks to all of you again. Thank you very much.
Thank you, Madam. Participants, if you have any questions or clarifications, you can ask now.
Can you hear me, Professor Rosana?
Yes, I can hear you, Professor Abbas. Thank you very much for your attention.
How are you?
Fine, thank you. I hope you